Lecture will go over more precise methods of determining the best fitting line to a prediction line to a set of data. Before we were kind of estimating from the graph. So this is the same data set we were working with before. We have data from 10 babies. We have gestation or length of pregnancy in weeks, and we have the birth weight in ounces. And because the gestation or the pregnancy comes before the birth, we'll make the gestation the X variable, and pregnancy, the birth weight the Y variable. Probably the length of pregnancy affects the birth weight. It might be a little bit of both, but we'll assume that the X variable is the gestation or the length of pregnancy. Okay, so what we want to do is the first step is to complete the mean and standard deviation of each variable separately. So this is like what we were doing in the first part of the course, computing the variance, but we couldn't compute the variance first for the X variable. Compute the mean, add up all the numbers, divide by the number of numbers. It's 39 weeks, and then each birth weight, or each gestation minus the mean, and then square it. 39 minus 39 is 0, 0 squared is 0, 40 minus 39 is 1, 1 squared is 1, and so forth. And you add these up, you get a total of 70, and then the standard deviation is going to be actually the square root of the variance. Be square root of 70 divided by 9. It comes out to be about 2.78 something. And then we do the same thing for the Y variable. I want to compute the mean for the Y variable, and the mean comes out to be 102 ounces. Add up all the birth weights, divide by 10 babies, and then each birth weight minus the mean, and then square it. So 104 minus 102 is 2, 2 squared is 4, and so forth. And the sum of the squares is 2480, and take the square root of 2480 divided by n minus 1, so it's 2480 divided by 9. Square root of that is 16.59 something. Okay, so now we have the mean and standard deviation of each variable, and then the next step is to compute the z-score for each baby for each variable. So for Quincy, Quincy's, I didn't show all the work here, but Quincy was born after 39 weeks. 39 minus 39 is 0. 0 divided by the standard deviation is 0. And then Quincy's birth weight was 104. The mean was 102. 104 minus 102, and then divide by the standard deviation comes out to be 0.12 something. And then you multiply the two z-scores together. So the z-score for Quincy, the z-score for gestation, times the z-score for the birth weight. That's 0 times 0.12 something, and that's equal to 0. So you do that for each baby. You compute the z-score for X for each baby, the z-score for Y for each baby, and multiply the two z-scores together. And then you add those up, I guess 8.2 something, and then here's the formula here. This is the z-score for X, that's the z-score for Y, so you multiply them together. Sigma for X, z-score for Y, multiply them together. Sigma means sum, so you add them up and then divide by n minus 1, so it's up 8.2 something divided by 9. And so the correlation is 0.912 something, a strong positive correlation. Okay, so then once we have the correlation coefficient, we can compute the proportion of variability. That's r squared. It's 0.912 something times itself, 0.83. And that gives us the percentage of the variance of the Y variable that can be explained by the X variable. So that's as a percent, it's 83% of the variance of the birth weight can be explained by the length of pregnancy. So the hardest part of the computation is the correlation coefficient. So that's quite a bit of computation. We have the mean. You want to compute the mean and standard deviation of each variable separately, and then compute the z-scores, multiply the z-scores together, divide by n minus 1, add them up, divide by n minus 1. So that's a lot of computation. Once you have once you have r, the correlation coefficient, then the slope is not so hard. And again, we have several letters representing the slope. Our calculator uses the letter A. Some statisticians like the letter A for the slope. Mathematicians like the letter M for the slope. Some statisticians use B1 for the slope. But in any case, whatever symbol it is, it's going to be R times the standard deviation for Y divided by the standard deviation for X. So R is 0.912 something, standard deviation for Y is 16 point something, divided by the standard deviation for X. It comes out to be 5.42 some ounces per week. And then the best y-intercept is some people use B, some people use B0 for the y-intercept, but it's going to be y bar, the best y-intercept, y bar minus the best slope times x bar, the mean for y minus the best slope times the mean for x. So you plug in the formula there, 102 minus 5.42 something times 39, and that comes out to be negative 109.7 some ounces. Okay, so that's that. Now we're ready to write the equation. Y equal ax plus b. So the y variable is birth weight equals slope is 5.42 something times the x variable, which is gestation, plus the y-intercept, which is negative 109.7 something. And then we can, so that's our equation for predicting birth weights. We can use this equation to predict the birth weights for each of the babies. So for Quincy was born after 39 weeks. Quincy's predicted birth weight, 5.42 something times 39 minus 109 point something is 102 ounces. Quincy's actual birth weight or observed birth weight was 104 ounces. So the residual or the prediction error is 104 minus 102, which is 2 ounces. So this is a closer prediction than we got with the scatter plot. In general, the scatter plot was going to have going to be less accurate. Here we get on the next step, we see that the predictions were closer for 7 out of 10 of the babies using the more precise formulas. Okay, so anyway, we get the residual for Quincy is 2 ounces, and then the residual squared is 4. The sum of the residuals should come out to be 0. If we add these up, it should come out to be 0. So we're more interested in the sum of the squared residuals, because that kind of relates to some of the theorems behind these computations. So you compute each residual, square it, add them up, and we get a total sum of squared residuals is 417. So with the scatter plot, our sum of squared residuals was almost 700. So this is a much better prediction by that standard. It's on the average, the prediction errors are going to be smaller with this slope and this y-intercept. And there's a theorem that there's no other line that we can fit for this data set that will have a lower sum of squared residuals. This is the best that we can do. Okay, so again, I went over this in the last lecture, but you can check your answer on the calculator, and it should come out to be exactly the same as what we had before, or at most off in the last digit. It might be off in the last digit because of rounding, but it should be pretty close to what we had from the formulas. Okay. And also want to mention that some of the WebAssign exercises will give you some computer output, and I ask you to identify the different statistics from the computer output. And so the computer output can be kind of cryptic. R squared, that's the proportion of variability, that's 0.83 or 83%. So you have to sort of read through this and sort of pick out what the information from the computer output. Where it says residual, this is actually the sum of the squared residuals. It's 417. That's what we got before. Where it says intercept, that's actually the y-intercept. That's b. It's negative 109.7 something. And x variable 1, that's the slope. So it's maybe not completely clear from the language here, but this is actually a slope. So this is b, and this is a, or m. This is r squared, and this is the sum of the squared residuals. Sum residual squared. Okay, so it's the computer output. Okay, so that concludes this presentation.